Swayam Prabha. Digital India. Educated India.
Welcome everyone to this lecture on multiple linear regression. In the preceding lectures we saw how to regress a single independent variable to a dependent variable. Particularly we were developing a linear model between the independent and dependent variable. We also saw various measures by which we can assess the model that we built. In this lecture we will extend all of these ideas to multiple linear regression, which consists of one dependent variable but several independent variables. So as I said that we have a dependent variable which we denote by y and several independent variables which we denote by the symbols xj, where j equals 1 to p. There are p independent variables which we believe affect the dependent variable. We will try to develop a linear model between the dependent variable y and these independent p independent variables x j equals 1 to p. In general we can write this linear model as before. We can say y, the dependent variable, is equal to a beta naught, an intercept, plus beta 1 times x1 plus beta 2 times x2 and so on up to beta times p xp, where beta 1, beta 2, beta p represents the slope parameters or the effect of the individual independent variables on the dependent variable. In addition we also have an error. This error is due to error in the dependent variable, measurement of the dependent variable. In ordinary least squares we always assume that the independent variable measurements are perfectly measured and do not have any error, whereas the dependent variable may contain some error, and that error is indicated as epsilon. We do not know what this quantity is, we assume that it is a random quantity with 0 mean and some variance. If we take the ith sample corresponding to this measurement of x1 to xp and y corresponding y, we can say that the ith sample dependent variable yi is equal to beta naught plus beta 1 x1 I, the ith sample value of the independent variable 1. Similarly x2i, beta 2 times x2i, where x2i represents the value of the second independent variable for the ith sample, and so on, plus an error I that corrupts the measurement of yi, and so on for I equals 1 to n. We assume we have small n number of samples that we have obtained, and our aim is to find the values, best estimates of beta naught, beta 1, beta 2 up to beta p using these n sample measurements of x's and corresponding y. This is what we call multiple linear regression, because we are fitting a linear model and there are many independent variables, and we therefore call it the multiple linear regression problem. Again, in order to find the best estimates of the parameters beta naught to beta p, we actually set up the minimization of the sum squared of errors. In order to set it up in a compact manner using vectors and matrices, we define the following notations. Let us define the vector y, which consists of all the n measurements of the dependent variable y1 to yn. We have also done one further thing, we have subtracted the mean value of all these measurements from each of the observations. So the first one represents the first sample value of the dependent variable y1 minus the mean value of y over all the measurements y bar. So the first sample is mean shifted value of the first observation. The second coefficient or second value in this vector is the second sample value minus the mean value of the dependent variable, and so on for all the n observations we have. So these are the mean shifted values of all the n samples for the dependent variable. Similarly, we will construct a matrix X where the first column corresponds to variable independent variable 1, again what we do is take the sample value of the first independent variable and subtract the mean value of the first independent variable. That means we take the mean of all these n samples for the first variable and subtract it from each of the observations of the first independent variable. So the first coefficient here will be x11 represents the sample value of the first independent variable, first independent variable minus the mean value of the first independent variable, and we do this for all n measurements of the first independent variable. Similarly, we do this for the second independent variable and arrange it in the second column. So this one represents the observation, the first observation of the second independent variable minus the mean value of the second independent variable, and we do this for all p variables, independent variables. So this particular matrix X that we get will be a n cross p matrix. N is the number of rows, p is the number of columns. You can view the first row as actually the sample, first sample of all independent variables for the first sample. Of course, we have mean shifted that value, and the second row is the second sample and so on, and each column represents a variable. So first column represents the first independent variable and the last column represents the pth independent variable. So similarly, we will represent all the coefficients beta except beta naught in a vector form, beta 1 to beta p as a column vector, here basically as a a row vector. So beta 1 is the first coefficient, beta p is the coefficient corresponding to the pth variable. So we have beta vector which is a p cross 1 vector. We can also define the epsilon, the noise vector, as epsilon 1 to epsilon n corresponding to all the n observations. Now having defined this notation, we can write our linear model in the form y equals x times beta plus epsilon. Notice that we have not included beta naught, we have eliminated that indirectly by doing this mean subtraction. I will show you how that happens, but you can take it that right now we are only interested in the slope parameters. This linear model only involves the slope parameters beta 1 to beta p, does not involve the beta naught parameter, because that has been effectively removed from the linear model using this mean subtraction idea. So we can write our linear model compactly as y equals x beta plus epsilon, and we also make the usual assumptions about the error, that it is a zero mean vector. In this case, because it is a multivariate vector, 0 is a vector. So epsilon, expected value of epsilon 0 implies epsilon is a random vector with 0 mean, and the variance covariance matrix of epsilon is assumed to be sigma squared identity. Sigma squared identity in this form, it means all the epsilons, epsilon 1 to epsilon n all have the same variance sigma squared, homoscedastic assumption, and we also assume that epsilon 1 and epsilon 2 are uncorrelated, or epsilon I and epsilon j are uncorrelated if I is not equal to j, in which case we can write the covariance matrix of epsilon as sigma squared I. Now under this assumption we can go ahead and say we want to find the estimates of beta so as to minimize the sum squared of the errors. So epsilon transpose epsilon is a compact way of saying the sum of all errors, error squared of all the errors in all the n measurements. So expanding this is nothing but sigma epsilon I squared I equals 1 to n, that is compactly written like this, and this is what we want to minimize, but epsilon itself can be written as y minus x beta. So we can write this whole thing as y minus x beta transpose y minus x beta. We want to minimize this, which is a function of beta, by finding the best value of beta. So if we set up this optimization problem to minimize the sum squared errors to find beta, we can show, we can by differentiating that objective function with respect to beta and setting it equal to 0, we get what are called the first order conditions, and these first order conditions will result in the following set of linear equations. We will get x transpose x into beta equals x transpose y. Now this is a p cross, remember x is a n cross p matrix, so x transpose is p cross n. So this is a square matrix, x transpose x is a square matrix of size p cross p and multiplied by the p cross 1 vector, and similarly it is p cross 1 on the right hand side. So these are p equations in p variables. there are linear equations in beta, x is all known, y is known. So right hand side is like the, if you interpret it as a times some x is equal to b. It is a set of linear equations, p equations in p variables, which can be easily solved if A is invertible. So we assume that x transpose x is a full rank matrix, invertible. The meaning of this will become a little clearer later, and if it is not invertible, we will have to do other things which we will again talk in another lecture. But for the time being, let us assume that x transpose x, which is a square matrix, is invertible, it is a full rank matrix, and then you can easily find the solution for beta hat, solve this linear set of equations by taking A inverse B, which is exactly x transpose x inverse x transpose y. So beta hat, the coefficient vector, can be found by this thing, and this is the solution that minimizes the sum squared errors, this objective function that we have written. So once we get beta 1, the slope parameters, beta naught can be estimated as the mean value of y minus the mean vector x transpose times the slope parameter. Notice that this is very similar to what we have in the univariate case, where it says beta naught estimate is nothing but y bar minus x bar into beta 1. So it is very similar to that, you can see. You can also compare the solution for the slope parameters for the with the univariate case, which says beta 1 hat is sxy divided by sxx. Notice that x transpose y represents sxy and x transpose x represents sxx. In the univariate case, you are dividing sxy by sxx. In the multivariate case, division is represented by the inverse, so you get x transpose x inverse times x transpose y. So you can see it is very similar to the solution for the univariate case, except that these are matrices and vectors, and therefore you have to be careful. You can't simply divide, it is matrix times inverse times a vector. That is the solution for beta, which is slope parameters. You can also estimate beta naught and beta 1 by doing what is called the augmentation of the x vector with a constant value 1 1 1 in the final thing, but I did not use that approach because the mean subtraction approach is a much better approach for estimating whether if for estimating beta naught and beta 1 slope parameters, because this is applicable even to another case called the total least squares. The augmentation approach is valid only for ordinary least squares, you cannot use it for total least squares, which we will see again later. So that is why I use the mean subtraction route in order to obtain the estimates of the slope parameter first, followed by the estimation of beta naught using the estimates of the slope parameters in this panel. Now you can also derive properties of these parameters beta. We can show that the expected value of beta hat is beta, which just means it is an unbiased estimate just as in the univariate case, and we can also get the variance of this beta hat. In this case it is a covariance matrix because it is a vector, and we can show that the covariance matrix is sigma squared times this x transpose x inverse. Now again you can go back and look at the univariate case, there the variance of beta 1, the slope parameter, will be sigma squared by sxx. In this case it is sigma squared into x transpose x inverse. So x transpose x represents sxx. Sigma squared is the variance of the error corrupting the dependent variables. We may have a priori knowledge sometimes, in most cases we may not be able to know this value of sigma squared, we may not be given this, so we have to estimate the sigma squared from data, and we will show how to get this. These two parameters that actually we can show, the first parameter says that the estimates of beta 1, the slope parameters, are unbiased. So beta hat, our unbiased estimator, is an unbiased estimator of the true value beta. Moreover, it can show that among all linear estimators, because beta hat is a linear function of y, notice that x transpose x inverse x transpose is nothing but a matrix which basically multiplies the measurements y. So beta hat can be interpreted as a linear combination of the measurements, therefore it is known as a linear estimator. Among all such linear estimators, we can show that beta hat has the least variance, therefore it is called a blue estimator or unbiased estimator with the best linear unbiased estimator. That is what blue represents, best in the sense of having the least variance. Now we can also estimate, as I said, sigma squared from the data, and that sigma squared estimate is nothing but the, after you fit the linear model, you can take the predicted value for the ith sample from the linear model and compute this residual yi minus yi hat, which is the measured value minus the predicted value for the ith sample, square it, take the sum over all possible samples, n samples, divided by n minus p minus 1. Again, if you go back to your linear case or univariate case, you will find that the denominator is n minus 2. Here you have n minus p minus 1 because you are fitting p plus 1 parameters, p slope parameters plus 1 offset parameter. Therefore, out of the n measurements, p plus 1 are taken away for the deriving the estimates, only the remaining things are the degrees of freedom or the variability in the residuals is caused by the remaining n minus p minus 1 measurements, and that is why you are dividing by n minus p minus 1, whereas in the univariate case you would have divided by n minus 2 because you are estimating only 2 parameters there. So you can see a one-to-one similarity between the univariate regression problem and the multiple linear regression problem in every derivation that we have given here. Now once we have estimated sigma hat, the variance of the error used from the data, you can go back and construct confidence intervals for each slope parameter. We can show that the true slope parameter lies in this confidence interval for any confidence interval you might choose, 1 minus alpha. Alpha represents like a level of significance. So if you say alpha is equal to 0.05, 1 minus alpha would represent 0.95. So that will be a 95% confidence interval. Okay. Correspondingly, I will find the critical value from the t distribution n with n minus p minus 1 degrees of freedom, and this represents alpha by 2, the lower value, probability value from the t distribution, and this is the upper critical value where the probability area under the curve beyond the value is alpha by 2. So n minus p minus 1 represents the degrees of freedom. Notice that in the univariate case it would have been n minus 2, very similar. So the confidence interval for beta j for any given alpha can be computed using this particular formula, and the term here SE of beta hat j represents the standard deviation of the estimate of beta hat j, and that is given by the diagonal element here of this quantity with sigma square replaced by the estimate here. So we have computed the standard deviation of the of the parameter beta hat j, estimated parameter beta hat j, by using the estimated value of sigma multiplied by the diagonal element of x transpose x. So we are picking the diagonal elements of the covariance matrix of beta parameters. Okay, that is all we have done. So this represents the diagonal element or the square root of the diagonal element, which represents the standard deviation of the estimated value of beta, which is what is used in order to construct this confidence interval. So every one of this can be computed from the data, as you can see, and you can construct. Now the confidence interval can later be used for testing whether the estimated parameter beta is significant or insignificant, as we will see later. Now we will can also compute the correlation between y and y hat, which tells you whether the predicted value from the linear model resembles or closely related to the measured value. So typically we will draw a line between the y, the measured value, and the predicted value, and see whether it is these things fall on the 45-degree line, and if it does, then we think that the fit is good. Another way of doing this is to find the correlation coefficient between y and y hat, which is simply using the standard thing, yi minus y bar multiplied by yi hat minus y hat bar, okay, summed over all quantities divided by the standard deviation of in y and the standard deviation in y hat. That is for normalization. We could also use the coefficient of determination r squared just as we did for the univariate case. We can compute r squared as 1 minus sum squared error by sum squared total, which is nothing but numerator is yi minus yi hat, the residual squared, divided by yi minus y bar squared, which is the variance in y basically. So if we take 1 minus this, we can show whether using the independent variables have we been able to get a better fit. If we have obtained a very good fit, then the numerator will be close to 0 and r squared will be close to 1. On the other hand, if we had not improved the fit because of x's, any of the x's, then the numerator will be almost equal to the denominator and therefore this one will be close to 0. So a value of r squared close to 1 as before represents indication of a good linear fit, whereas a value close to 0 indicates the fit is not good. We can also compute adjusted r squared to account for the degrees of freedom. Notice that the numerator has n minus p minus 1 degrees of freedom, whereas the denominator has n minus 1 degrees of freedom. Therefore we can do an adjusted r squared which divides the SSE by the appropriate degrees of freedom. We can say this is the error due to per degree of freedom that is there in the fit, whereas the denominator represents the error because we have fitted only the offset parameter. There are n minus 1 degrees of freedom, this is the error per degree of freedom. So this kind of a thing is also a good indicator. Instead of using r squared, we can use adjusted value of r squared. So these are all very similar again to the univariate linear regression problem. So we can use we can check r squared and see whether the value is close to 1, and if it is, we can say maybe the linear model is good to fit the data, but that is not a confirmatory test. We have to do the residual plot as we did in linear regression, univariate linear regression, and that is what we are going to do further. So we are going to find whether the fitted model is adequate or it can be reduced further. What this reduced further means we will explain. In the univariate case there is only one independent variable, but here there are several independent variables. Maybe not all independent variables have an effect on y. Some of the independent variables may be irrelevant. So one way of trying to find whether a particular independent variable has an effect is to test the corresponding coefficient. Notice we have already defined the confidence interval for each coefficient, and we can see whether the confidence interval contains 0, in which case we can say the corresponding independent variable does not have a significant effect on the dependent variable and we can perhaps drop it, okay. Or we can also do what we call the test, F test, just as we did in the univariate regression problem. We can test whether the full model, okay, is better than the reduced model. The reduced model contains no independent variables, whereas the full model can contain all or some of the independent variables. You can do many kinds of tests and we will do this. So we can test whether the reduced model, which contains only the constant intercept parameter, is a good fit as opposed to including all the independent variables, some or all the independent variables. That is what we call the full model. We will consider a specific case here where we do the F test statistic for the case when we have a reduced model and compare it with the full model. The reduced model we will consider with k parameters. Specifically, let us consider the reduced model with only one parameter, which means that we have only the constant intercept parameter. We will not include any of the independent variables, and compare it with the full model which contains all of the independent variables, okay, including the intercept. So the reduced model is one which contains only the offset parameter and no independent variables. The full model is the case where we consider all the independent variables and the intercept parameter. So the number of parameters we are estimating in the reduced model is only 1, so k equals 1, and the full model is the case where we have all the independent variables, p independent variables, so we are estimating p plus 1 parameters in the full model, okay. So what we do is perform a fit and compute the sum squared errors, which is nothing but the difference between y, the measured value, and the predicted value. So we will first take the model containing only the offset or the intercept parameter and estimate. In this case, of course, y bar will be the best estimate and we will compute sum squared errors, which is nothing but the variance of the measurements for the dependent variable. Then we will also perform a linear regression containing all the parameters independent variables, and in this case if we compute the difference between y and y predicted and take the sum squared errors, that is the SSE of the full model. So when we want to compare whether we want to accept the full model as compared to the reduced model, what we do is take the difference in the sum squared errors. Remember, the sum squared errors for the reduced model will be greater than the sum squared errors for the full model, because the full model contains more number of parameters and therefore you will get a better fit. So the difference in the fit, which is difference in the sum squared errors between the reduced model fit and the full model fit, that is the numerator, divided by what we call the degrees of freedom. Notice the full model has p plus 1 parameters, p independent variable plus the offset, and the reduced model in this particular case contains only one parameter, so k equals 1. So the degrees of freedom will be p. So you divide this difference in the sum squared errors by p. Denominator is the sum squared errors of the full model, which contains n minus p minus 1 degrees of freedom, because p plus 1 parameters have been fitted. Therefore the degrees of freedom is the total number of measurements minus p minus 1, and so we divide the sum squared errors for the denominator by the number of degrees of freedom, and then take this ratio as defined, and that is your F statistic. Now in order to reject, if we want to reject the null hypothesis, or if we want to test the null hypothesis against this alternative, we find the test criteria for the alpha level of significance. We will take it from the F distribution, where the numerator degrees of freedom is p plus 1 minus k. For this particular case it is exactly p, and the denominator degrees of freedom is n minus p minus 1, and alpha level of significance we use, and we compute the test criteria, critical value from the F distribution. Then we compare the test statistic with the critical value, and if the test statistic exceeds the critical value at this level of significance, then we reject the null hypothesis. That is, we will say the full model is a better choice and the independent variables do make a difference, and this is a standard thing that an R function will provide. This particular comparison between the reduced model, which has no independent variables, and the full model, which contains all the independent variables in multilinear regression. Of course you can choose different reduced models and compare with the full model. For example, you can take the reduced model by leaving out only one of the independent variables, so that will have p parameters. We can compare it with the full model and again perform a test to decide whether the inclusion of that independent variable makes a difference or not. So this kind of combination can be done depending on what stage you are, and that we will be using in what we call the sequential method for subset selection, that will be discussed in a later lecture. But essentially the R functions only provide a comparison between the reduced model, which contains no independent variable, and the full model, which contains all of the independent variables. Okay, let us go through a simple example in order to what we call revisit these ideas. So in this case we have what is called a price data, where customers have been asked to rate the food and the other aesthetics of a particular restaurant, and we also and the cost of the particular dinner, also data were obtained for these restaurants, and the location of these restaurants, whether they are on the east side of a particular street in New York or the west side. Typically in New York, the west side is probably a little poorer, whereas the east side probably is a little richer neighborhood. So location of the restaurant also would indicate would have an effect on the price. So these are the 4 independent variables people data was obtained on: the quality of the food, the decor and service. All this was rated by the customers, and at the location of this restaurant, and the price of dinner served in that restaurant was also taken. So you would expect that the quality of the food, the service level, all of this would have a very direct influence on the price in the restaurant, and a linear model was built between y and the independent variables x1 to x4. So before we build a model, we do a scatter plot as usual in visualization, and here because there are several independent variables, we have not just one plot, scatter plot between y and x1. For example, in this case remember price is y versus x1. This particular plot shows the correlation or the scatter plot for y versus x1 or y versus food, price versus food. The second one is the scatter plot between price and decor. The third one is the scatter plot between price and service, and the last one is price versus location. Okay. And similarly you can actually develop a scatter plot between food and decor, which is here, or food and service, and so on. Even though we consider all these variables that we have obtained like food, decor, service, location as independent, it is possible when we select these variables they are not truly independent. There might be interdependencies between the what we call the so called independent variables that can give rise to problem in regression, which we will see later, the what we call the effect of collinearity. But a scatter plot may reveal some dependencies, interdependencies between the independent so called independent variables. So for example, if we look at the scatter plot between food and decor, it seems to be completely randomly distributed. There doesn't seem to be any quite correlation. However, food and service seems to be very strongly correlated. There seems to be a linear relationship between food and service. So perhaps you don't need to include both these variables. We will see later that it is true. But in this, just the scatter plot itself reveals some interesting features, and so we will now go ahead and say, okay, perhaps a linear model between price and food and decor seems to be pointed out or indicated by the scatter plots. Let's go ahead and build one, and if we apply the R function LM to this data set and we examine the output, we will get this output from R, and it tells that the intercept term is minus 24.02 and the slope parameters, the coefficient multiplying food is 1.5, the coefficient multiplying decor is 1.9, and so on and so forth. It also gives you the standard error for each coefficient as well as the offset parameter, which is nothing but the sigma value for the estimated quantities, and it also gives you the probability values, p values as we call them. And notice, if the p value is very low, it means that this coefficient is significant. We cannot take it that this value is 0. Okay. Any low value of this indicates that the corresponding coefficient is significantly different from 0. So in this case the first three has very low p values and therefore they are significant, but service has a high p value, therefore it seems to indicate that this coefficient is insignificant, is almost equal to 0. That is what this indicates. If you look at the east, which is this independent location parameter, that doesn't have a very low p value, but it's still not bad, 0.03, and therefore it is significant only, is insignificant only if you take a level of significance of 0.025 or something like that. If you take 0.1 or 0.05 and so on, you will still consider this east this coefficient to be significant. Okay, and that's what this is basically pointing out. The star indicates that. Okay, so now we'll go ahead and try to actually look at the f value also. The f statistic says that the full model, okay, as compared to the reduced model of using only the intercept, is actually significant, which means the constant model is not good, and including these variables results in a better fit or explanation of the price, and therefore you should actually include this. Whether you should include all of them or only some of them, we can do different kinds of tests to find out. What we have done in this particular case is only compare the model without any of these independent variables, which is called the constant model, with all of these variables included. That is the only two model comparisons we have made. The reduced model is one containing only the intercept term, and the full model is one which contains intercept and all four independent variables, and that is the p value it has given, the corresponding f statistic. So we are saying that including these independent variables is important in explaining the price. Okay, so but it may turn out that all of them is not necessary, and that we will examine further. So the corresponding fit that we obtain is this. As I said, that from the what you call the confidence interval for for the slope parameter for service, we can say that we can remove this, it is insignificant and perhaps we can remove this and try the fit. For the time being, let us actually remove this and try the fit. We have done that, we have only included now food, decor and east and done the regression again, and it turns out that the regression thing is still what you call the R squared value is improved, not improved significantly but not reduced, and F value is significant, and we get the more or less the same coefficients for the other parameters also, the intercept term and the slope parameters. It indicates that x3 is not adding any value to the prediction of y. The reason for this, as we said, if you look at the scatter plot, service and food are very strongly correlated, therefore only either food or service needs to be included in order to explain price and not both, right, and in this case service is being removed, but you can try removing food as the variable and try to fit between price, decor and decor, service and east, and you will find that the regression is as good as retaining food and eliminating service. R squared value and the F statistic seems to indicate that we can go ahead with the linear model, but we should further examine the standardized residual plot for concluding whether the linear model is okay or not. There should be no pattern in the residuals. So let us actually do the residual plot. Here we have taken the standardized residuals and plotted it against what is called the predicted price value or the fitted value. Remember, this is yi hat. Yi hat is only one variable, so you need to generate only one plot, and we have also shown here in red lines the confidence interval for the standardized residuals, and anything above this outside of this interval indicates outliers. So for example 56, sample number 48, sample number 30 and 109 and so on and so forth may be possible outliers, and but there is no pattern in the standardized residuals, it is spread randomly within this boundary, and therefore we can say, since there is no pattern, a linear fit is acceptable. So here the quality of the fit is shown here. So the actual price measured value versus the yi hat predicted value is shown, and a linear model seems to explain the data reasonably well. The last thing is, we have these outliers. If you want to improve the fit, you may want to remove, let us say, the outlier which is furthest away from the boundary. For example, you may want to remove 56 and redo the linear regression, multiple linear regression, and again repeat it until there are no outliers. That will improve the R squared value and the fit, quality of the fit a little more. Okay. So we have not done that, we leave this as an exercise for you. So what we have done is, we have seen that whatever was valid for the univariate regression can be extended to the multiple linear regression, except that scalars there will get replaced by vectors and matrices corresponding. What was a variance there will become a variance covariance matrix here, what was a vector there, scalar there might mean scalar might become a mean vector here. So you will see a one-to-one correspondence, but the residuals plot and interpretation of confidence interval for beta, all of this, the F statistic are more or less similar, except that understand in the multiple linear regression there are several independent variables, all of them may not be relevant. We may be able to take only a subset, and I will actually handle subset selection as a separate lecture. For the time being, we have just done a significance test on the coefficient in order to identify the irrelevant independent variables, but there are better approaches and we will take that up in the following lectures.